Hey, 2 more weeks before the midterm. Today we will talk about share coding, how to write a share code. I will give you a few examples, then give you more challenges. You will develop your own share code in the class. Next class, probably we will spend half of the class on share coding. Then we talk about format string vulnerability. You already know what is share code. You have been using several share code. The one actually returns a share, the one that reads the file and print it out. You have 32-bit version of the share code, 64-bit version of share code. But share code, as you can see, is basically code, instructions. So you can do anything with it. It doesn't just need to do what we have been doing. So there have been several books talking about developing share code. Some of the books are quite old. So those are the books I used when I started learning, but they have been there for 15 years or maybe even older. So today we're going to learn what else can share code do. Like I said, you can do anything with it. Then we will make some more injectable share code. We will add all kinds of constraints on the share code. There will be a tester with all kinds of constraints. Then you will develop your share code to pass those kind of limitations. So far, the share code you guys have been using, we can classify them as local share code. You need local access to the computer to get that, to run the share code and get a shell or capture the flag, right? So this is the 32-bit version you have been using. This is a 64-bit version you have been using. Basically, it makes two system calls. The first one is open, and we are trying to open the flag file in the root directory. That's why we have /flags there. But if you run that program in the root directory, then you do not really need that slash there, right? Because it's more like we're trying to find the flag file in the current directory. After we open that, we just send the file to std out, which has a file descriptor 1. Okay, that's what we are doing in this shellcode, two system calls. So this is different from open, read, then write. If you do that, you need 3 system calls, which also works, but this one will be a little bit easier. Then we can also develop remote shellcode that can give you a share across the internet. There have been some examples. Let's say the first one. So when you develop a share code, you basically develop in assembly language, right? Then how do you develop a remote shell? You basically want to create a shell, then bind the input, the std in of that shell to a network socket. So the network socket will take input from some remote party. Then that input is fed into the shell. Okay. So if you develop this in C code, it will look like this. And the developing shell code is more like maybe you can compile this, then get the machine instructions, and that will be a shell code. Or you can develop in assembly language, do something similar to this, right? So at the C code level, the logic is like this. You create 2 socket numbers, then use the socket API, which also is a system call. So this here obviously is a C library function, but eventually it's a system call. This system call will create a socket. And we say this socket is an internet socket, and we're going to use TCP in this case. Then we need to code an address. And this is a C structure socket address in, we said the family is internet. The source address there doesn't really matter, means whoever, anyone can click to this. Then we have a port number here. This is a port number we're going to listen. Then we bind this socket file descriptor with this address. then we just listen at this file descriptor. So this is how you develop a web server at a socket level. You listen at a socket, okay? And the 5 here means how many collections can be in the waiting queue here. So this number is not very important here. So well, after you listen, you can accept collections from a remote party. When you accept a new collection, so all of this actually they are system calls. This accepts system call will create a new file descriptor. Then there are 2 file descriptors. One file descriptor is to listen, which is binding with this port number. Another file descriptor is the new collection, which doesn't need to bind this port number. Okay. So after that, we will duplicate this file descriptor, which is a new collection. Then we will, in this case, we're actually so I is 2. Then we are getting I from here it actually is 3. Sorry, I starts with 2, then eventually gets to 0. So 0, 1, 2, right? So we will duplicate this new file descriptor, which is for that collection, to the file descriptor of 0, 1, 2. Okay, what are those file descriptors?
Standard in, standard out, standard error.
Exactly. So we are putting this socket, collecting the socket to standard in, standard out, and standard error. So then, which means this program's input output will all go to that socket. Okay. Then after that, we just create a new process, which is our shell. So that is the logic behind this port binding remote shell. So if you program this, it will be how many bytes? Maybe 100 bytes, not very big. C code level, 25 lines of code. Byte level, maybe 100 bytes or smaller. Then you can get a port binding shell. Sometimes you may not be able to bind any port, right? Because there may be a firewall. The firewall blocks blocks you from using a new port. Then in the book, this is very old technique, is you can bind to some existing port. You do not have to create a new port. In the previous example, we create a new port, 1, 2, 3, 4, 5, which is a big number. Some firewall may block that. You can actually bind to an existing port. And this piece of shellcode is not even trying to create a new socket using a port number. It will just find an existing port that is in use. Then we use that port to connect to the shell. Then we reuse that port. Another example, a reverse connection shellcode. In this example, we have the compromised machine tries to connect to the attacker's machine. Okay, in the previous example, the compromised machine will run listen and accept. So it's the server side of the TCP. Okay, so in this example, the attacker will run a server on his machine. Then the victim, the compromised machine, will play the role of the TCP client. Instead of listen and accept, it will try to connect to a remote server. Okay. So in this case, the attacker's IP address is hard-coded here. The attacker is listening on this port on the attacker's machine. Then this piece of shellcode will try to make a TCP connection, send the TCP SYN packet to the attacker's server. Okay. This is also useful for depending on what kind of firewall policy you are trying to bypass. In some cases, the firewall will not allow the victim, the compromised machine, to make outgoing connections. Sometimes it doesn't allow the outside to make ingoing connection requests. Then we just duplicate those to different STD in, STD out, and STD error. Then execute the share. Okay, the same idea here. So those are the three remote shellcode. So those are examples to show that shellcode can do anything. Basically machine code. Most of them are small because it's not easy to program in assembly level, but they are Turing complete. They can do anything. So next we can see more examples of shellcode that is more injectable and also disableable. One of the papers I want to mention is this one. This is one of the papers I read when I started my PhD. The paper was published in ACM CCS 2009, one of the top security conferences. And the title of this paper is just English shellcode, 2 words. Okay. The idea of the paper is very simple. On 4 x86 machines, 32-bit, 64-bit machines, they developed an automated system to generate shellcode or translate existing shellcode to readable English. Not necessarily high quality, but readable English. Okay, this is before ChatGPT and everything, not before that, 15 years before that. Okay. So here is one example. So the bottom, we have a paragraph in plain text English. It reads like there is a major center of economic activity such as Star Trek, including the Ed Sullivan show, blah, 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 right? Okay, so this is readable English. May not make much sense to most of us, but this piece of English, if the CPU start executing at the beginning, there are valid instructions. So there is a major, so that is basically 5 instructions there. 2 pushes, 1 multiplication, another push, and a jump. Okay. So this part is this part. The ASCII are those 5 instructions. Then the next part is just some padding. We are going to jump. We are going to skip this part. Okay. So they are just to make this paragraph more readable. So the second part is this H white space of star. Those are another 4 instructions. Right? So you can imagine this can be used to exploit vulnerabilities in instant messengers. Someone is chatting with you, but actually is trying to exploit you, exploit the vulnerability in your instant messenger, right? So this is English shellcode. Then several years ago, there was a paper, DNA shellcode, which I feel is a very cool idea. This is a very cool idea. This paper was from University of Washington. So what they did is, so first of all, what is DNA here? There are only 4 different types, right? AC, ACGT here. So your shellcode can only use AC, ACGT, 3 letters. That's it. Only those 4 letters. And they embedded a buffer overflow bug in a DNA file analyzer. It's a program, and that program takes the FASTQ file as input. Okay, FASTQ file is a file that have all kinds of DNA strings. There can be a little bit of metadata there, like timestamp, which machine this is generated, but this is a text file format. Okay, the main thing in this file format is those DNA strings, only those 4 letters. And there is a software to process this data, and that software, they embed some buffer overflow there. Then what they did is they developed a shellcode. Then they encode that shellcode just using that ATGC, those 4 letters. So for example, this is their shellcode. And after encoding, it will look like this. Then they synthesized this into real DNA. There are companies online can synthesize DNA for you, but there are a lot of restrictions. Not the restriction here is not just only you can only use those AGTC, those 4 letters. Some of the DNAs cannot be synthesized. They're not stable. They cannot. Okay, I'm not a chemist. I don't know why, but they cannot. But there are a lot of constraints. So you also need to bypass those kind of constraints. Then after that, they get this tube of DNA. Then they put this DNA into this DNA sequencer, eventually generate this FASTQ file, then input into the software, and the software has a buffer overflow vulnerability, and eventually execute the shellcode. So this was published in Usenix Security 7 years ago, another top conference in our area. So this Professor Yoshi has done a lot of cool research. If you visit his website, he's among the first to hack cars, the first to do DNA hacking, the first to do hacking virtual reality devices. Yeah, a lot of cool research from his group. Okay, so in the rest of class, we will develop our own shellcode. We are going to use a template as simple as this. In this class, we use Intel syntax. So this is just an assembly file. At the beginning of the assembly file, you can use this command, directive.Intel syntax, no prefix, to say I'm going to use Intel syntax here. Then you can create a global entry point _ star. Then you can have your instruction here, as simple as this. So how do we compile this? You can use those GCC commands to compile that. First, you use GCC for 32-bit version. You need to use machine 32-bit. Your code is not going to call any library, so you do not need standard library. So just say no stdlib. It should be statically compiled because you're not going to use dynamic library anyway. Then you have your assembly code. The output will be an L file. This is an L file, okay? So L file has all kinds of metadata. You don't really need those metadata. What you need is just the .text section, those instructions, right? So there is another ELF tool, which is obj copy. In this class, we'll be using obj dump. So there's another tool called obj copy, and we use this tool to just copy the .text section, which is your instructions. Okay, so if you want to do this locally on your computer or on our server, you can follow those commands. But an easier way to do this is just to use web-based tools. Yeah, so a lot of web-based tools out there. The first one is, I think it's blocked, but the second one and the third one you can use. The second one, I think we used this last week. The third one is just a GCC or GDB online, okay, which will help you debug the program or shellcode. On our server, there is a shellcoding category, and there are many testers. So the source code of those testers look like something like this. Okay. So this is the very first one, no constraint. This one, you can have anything in your shellcode. Go ahead.
What would be the benefit of using the online compilers rather than just compiling on our machine.
You don't need to do all those commands. And you can just copy your mouse, will be much easier. Yeah. So this is a tester. This one has no constraint. So this program will first create a page. A page is like 4 KB on the machines in the memory. Then whatever your input is, you will input from std in to this program. So you just need to create your shellcode, then pipe your shellcode into this program. Then this program will read your input to that page, then start executing from that location. The way we are executing at a C code level is so this page is basically an address. We change that address to a function type. Then we call that function, right? So so this void star here means this is a function type. We're changing this to a function, and we just call this. So basically, by doing this, we're executing your shellcode. So this is one with no constraint, which means the current shellcode you have 2 copies, 4 copies of them, and you can use this, can pass this. Then there is a no zero version of this, which I do a string copy of your input to the page. Because it's a string copy, it will stop at 0, which means if you have a 0 in your shellcode in the middle, we're not going to copy all of your shellcode. So eventually it will crash, right? But this one, the shellcode I gave you guys already can also pass this one. So this is not what you're going to do. Well, the first one we're going to develop is this one. ASCII int 80. So for this one, we can do 32-bit version. You can only use ASCII characters in your shellcode with an exception. The exception here is you can use the instruction int 80, which has a machine code of CD and 80. Those CD and 80 are higher than 7F. Okay, so it's not really ASCII code anymore. That's an exception, which means you can still make a system call directly. So this is the easy one. What you can do is you change existing 32-bit version of shellcode, the one which is 21 bytes or something, remove those characters, letters that are bigger than 127, okay? Change those, but you can still have system calls. So this is the first one we're going to work on today. I will be walking in the room to help you guys. Some hints here. For 32-bit version, you run, the system call is int 80, and you put the arguments here. So all of this all of those information you can find online. Just the Google Linux system call table. It will show you 32-bit and 64-bit of the calling conventions for system calls. For 64-bit, similar, but you do not have to use int 80. There is a special instruction for that, syscall for that. 64-bit version writing a shellcode or writing assembly code in general is easier because you can do something called RIP-based addressing, which you cannot do at a 32-bit version. That's why we're only doing 1 or 2 32-bit versions, then we switch to 64-bit versions because it's easier actually. One example here. Here, we're trying to use a string here. We want to use the address of that string. And that address of string at assembly level, you can just get by this RIP plus the label of that string. Okay. This is not possible at a 32-bit version. 32-bit version, you cannot directly use EIP in the instruction. So after we finish that one, we are going to do a more challenging one. That one, we will allow all bytes except those system call bytes, which include syscall, int 80 and sys enter, those three instructions. So you cannot directly use those three instructions in your shellcode. But obviously your shellcode has to make system calls. Okay, so later you figure out how to do this. Okay, so after that, we're going to do another one. I think we will finish at least the first two today. So basically 3 shellcode challenges today. The last one we're going to finish today will be closed std in, std out, and std error. There's no constraint on your shellcode itself. It can have any bytes. However, the std in, std out, and std error are closed. Okay? You're not supposed to use them. Which means your shellcode, even if your shellcode can read the file, it cannot send the file because there is no std out. Okay. So how do you do? How do you still capture the flag here?
Put it in some other file,
Okay.
so then we can't do that.
How do you put in other file? Other file you still need to open that file and write to that file, right? Yeah.
Socket.
Socket is also a file. Yes.
Write it somewhere on the stack and use that in a.
Write somewhere on stack.
Yeah.
How do you read that?
Careful.
You can try. May not work. Okay, so for this one, I will need you guys to think out of the box. Do you? Yeah. Share pipe. Share pipe. That's also a file. Yeah. Do you really have to? Your goal is to steal capture the flag in that file. Does your shellcode really need to read that file and output that?
Change the permissions of the file.
Yeah, exactly. That's one of the approaches. Yes. So how do you change the permission? At the command line, how do you do that?
Change mode.
Change mode, right? And there is a system call corresponds to that change mode. So instead of open and send file, you will just make a system call to change mode. Then that file on file system, the permission is changed. Then you can just catch that. Okay, so that's one way to do that. Hopefully next week we're going to make your shellcode smaller. So right now I think it's 20 something bytes. Okay, we change it to first we make it 18 bytes, then 12 bytes. Okay. There are some challenges online. You need to do it with 6 bytes. Yeah. Obviously, if you do 6 bytes, you cannot make system calls like open and send file. Yeah, those system calls already is 4 bytes. You try to maybe make one system call, do that permission change thing. Only one system call. Then we will do a unique, which means each byte of your shellcode must be unique. Okay. Then we will have a sort. Your shellcode will be sorted byte by byte. Okay. Which means to make sure your shellcode will not be sorted, then your shellcode should already be from ascending order from small number to big number. Okay. Cool. So those are what we are going to do today. I would suggest you to just use this online tool to make things easier. Let me see. Yeah. So what you can do is you can copy our existing shellcode. So let's say we're going to work on the ASCII 32-bit first. Then this is shellcode, we know it works, right? So we just copy this one. See if there are white spaces. Okay, looks good. Then you just copy it here. 32 bits. You disassemble this. No. We disassemble this. Not even in the bytecode here. So those are the instructions. Then you can copy this part to the assembler part. Try to assemble this. Then you just change those instructions one by one. Make sure every byte fall into 0. No, you cannot do 0. Fall into 1 to 7F. But you can use this int 80 here, which is CD 80. You can even make this a little bit smaller because this shellcode has 3 system calls. The last one is exit. Okay, so you don't really need the last one. You only need from here to the top. Let's say here I say C0. C0 is not allowed. So here is a C0, B0. What are those actually? C0, B0. Let's go here. Oops.
X or DAX, DAX.
Yeah, let me get a bytecode here. Yeah, so C0 actually is the second byte of that exclusive EAX, which means you need to find another way, an equivalent instruction to do that, but do not use C0. Then B0 is move AL 5 to AL. You also need to change that. Yeah, let's start working on this. We can spend maybe 25, 30 minutes on this, and we'll move to the next one.